Okay, hello and welcome to this talk. My name is Tobias Christiani and I'll talk about the paper Confirmation Sampling for Exact Nearest Neighbor Search, which is joint work with Rasmus Pagh and Mikkel Thorup. So the outline of the talk is that I'll talk about a nearest neighbor search algorithm that A is able to stop at the right time. So it's searching and searching and searching for the nearest neighbor, but when should it stop? And this is the first question we will deal with. The second question is, or the property, the desirable property of the nearest neighbor search algorithm is that it should be able to adapt to the hardness of the query. And this will become clear later. So these two thought bubbles here, you have a search algorithm, it's searching, it's continually looking at examples in a database, but it wants to know, have I found the nearest neighbor yet? So is it okay to stop searching? And another thing which is about this adaptivity is the question of how carefully should the search algorithm look, essentially what magnification should it use, or what resolution should it look at, how much energy should it expect to use in the search. Okay, so this talk is about these two topics in search algorithms within the context of a group of search algorithms based on locality sensitive hashing. So defining the problem from the basics, the problem of nearest neighbor search, we're giving a collection of n data points, the black dots here in the illustration. And then we're supposed to pre-process these data points into a data structure that supports nearest neighbor queries. So we're given a query point Q, and we want to return the closest point to the query. So in this illustration here, that's x1. And for this talk, we'll be in the high dimensional setting. So the set of points is in a d-dimensional space where d is at least logarithmic in the number of points in the data set. And typical distances are Euclidean distance, angular distance, also known as cosine similarity, and the L1 distance. Okay, unfortunately, nearest neighbor search is known as a hard problem. So if you look at this example, and I ask you to tell me which of these points is the nearest neighbor to Q, you would essentially have to inspect every single point and measure them. But in fact, one of them is closer, even though they all look the same. And this is sort of an intuition about the hardness of nearest neighbor search. And this intuition has actually been formalized into a number of conditional lower bounds. And these lower bounds show that sublinear, so strongly sublinear query time, so that's impossible even with polynomial preprocessing time and space, unless something called the strong exponential time hypothesis is false. And another explanation for the hardness of nearest neighbor search, a typical explanation, is something called the Curse of Dimensionality. And this sort of shows itself by the fact that low dimensional techniques for nearest neighbor search do not scale well to high dimensions. So this is sort of to introduce the fact that nearest neighbor search is hard. But if we look at nearest neighbor search in practice, or approximate nearest neighbor search, then we measure the performance of these algorithms by their recall, which is the fraction of the true k nearest neighbors they return. And it turns out that there are a lot of different algorithms and a lot of different heuristical techniques that solve nearest neighbor search efficiently on real data sets. So they do much faster than linear scans or looking through the entire database. And this graph here is from the ANN benchmarks project. And it shows on the y-axis the number of queries per second, and on the x-axis the recall. And you can see that a lot of these algorithms are able to achieve good recall on I think this data set has 1.2 million points. So they achieve like recall 0.5 or 0.7 with thousands or up to tens of thousands queries per second. So this is much faster than a linear scan. So the explanation for this is, of course, that on real data, queries are often much easier than this hard worst case instance I showed you earlier. And the query complexity depends on the distances between the query point and all the other points. So typically, easy queries have the nearest neighbor much closer than non-nearest neighbors. Okay, so this sort of introduced the nearest neighbor problem, and now I'll talk about the solutions to these two problems using locality-sensitive hashing-based techniques. So the first problem is, when we are searching for nearest neighbors, when should we stop? And the solution that we propose is called confirmation sampling, something we call confirmation sampling. Another problem is sort of adapting to the hardness of the query, so adapting the search algorithm to whether we're in this easy instance over here or in the hard instance on the right. Okay, so let's first define locality-sensitive hashing. And locality-sensitive hashing is simply a distribution over functions that partition space such that close points are more likely to end up in the same partition. So another way of saying this is that if we have 2 points and we sample a hash function from a locality-sensitive distribution of hash functions, then the collision probability or the probability that these 2 points collide under the locality-sensitive hash function is increasing, or is non-decreasing in their similarity. Okay, so typical locality-sensitive hashing-based data structures for nearest neighbor search pre-process the data set into buckets. So they use locality-sensitive hashing to partition a set of points. So here's an example. We have our set of points on the left, and what we do is that we draw a locality-sensitive hash function and partition space. So now the bucket associated with the query point Q is all the points to the top of this line, which partition space. And this partitioning can be done multiple times, so we can concatenate several such partitioning or hash functions. So if we draw another locality-sensitive hash function, we sort of reduce the size of the bucket. We make it more discriminative, you could say. So on the right here, you can see that this defines a binary tree over the partitions. And we, of course, we can run this many times and we get a large tree called an LSH tree. But now we have separated the query point and the nearest neighbor. Okay, so the data structures we'll be considering here in this talk is a collection of such independent LSH trees. And the key to efficient search is to balance the number of buckets we should search and also the bucket resolution, so the depth that we want to search at in this tree. So we want a depth such that we don't get many collisions with uninteresting points, but we also want to be able to find the nearest neighbor reasonably fast. Okay, but remember these 2 problems I started talking about. So the problem of knowing when to stop, and then the secondly is the problem of adaptivity, or choosing the right depth to search at. So if we focus on the first problem, we consider that searching in a sequence of independent buckets. So we fix the depth. So for example, to 1, so we just have different independent partitions of the data space, and then we search the buckets associated with the query points. So this essentially corresponds to searching in an expanding ball around the query point, so sort of a probabilistically expanding ball, you could say. And let me just demonstrate what such a search algorithm could look like. So imagine this colored line here, or stripe, I guess, as being the part of space associated with the first bucket. So in this bucket we have 2 points, and the closest one we'll set that as our candidate for the nearest neighbor so far in the search. So it's the best point we've seen so far. So we may continue the search. So we look into another bucket. Okay, there are no points in that, so we haven't really made any progress. And we continue and find a third bucket, and we see here, okay, there's a point that's even closer to our query point, so perhaps that's the nearest neighbor. And this continues, and we may update the candidate and so on. But the question is, when is it okay to stop? When do we have actually some guarantee that we have found our nearest neighbor? So in this example, we never actually encountered the nearest neighbor. So stopping now would be wrong, you could say, or would not report the exact nearest neighbor. So one idea, which is the main idea behind confirmation sampling, is to keep track of the best candidate, so this beta, and then terminate once you see it again. So once you see it in a newly sampled bucket. And it turns out that this actually is able to recover the nearest neighbor with probability at least 1/2. Okay, let's now take a closer look at this idea of confirmation sampling. So we'll introduce it as a general algorithm for identifying the minimum element of a discrete distribution. And on this discrete distribution, on the support of the discrete distribution, we have a strict total ordering relation. And for running our algorithm, we only have access to samples from the distribution and to the ordering. So we're able to compare samples, whether they're smaller or larger than another. So we proceed as follows. We draw samples from the distribution, and we keep track of the minimum element sampled so far. So you could say the best candidate beta, as on the previous slide. And then we stop once beta has been confirmed or sampled t times, during which we didn't sample an even smaller element. So here you see the confirmation sampling algorithm pseudocode. So it takes as input, the distribution, and t, a parameter for the number of confirmations before stopping, and then the total ordering operator. So to go through the code briefly, we start by initializing the candidate to infinity and the count of the number of confirmations to 0. And then while the number of confirmations is less than t, we keep sampling. And if the sample is equal to the candidate, then we increment the count. And if the sample is smaller than the candidate, then we update the candidate to equal the sample and reset the count. And of course, here we are interested in the application of confirmation sampling to nearest neighbor search, specifically using locality sensitive hashing. So here we have that each sample, so each sample that we draw from the distribution is the closest point in our bucket created by LSH. And the total ordering is induced by the distance between the distance to the query point. So closer points are of course better. So let's take a look at running this algorithm on a small example. So now we're back to the general case, you could say. Here we set the distribution to be the uniform distribution over the integers from 1 to 9. And we set our ordering operator to be the standard less than operator. And in order to stop, we will require t equals to 2 confirmations. Okay, so now we'll see how the algorithm runs as we draw samples. We initialize, beta to infinity and the count to 0. And then we draw a sample. So here we drew a 7. So now we update our candidate beta to 7 and we reset the count to 0. Now we draw a 5. So the best candidate is updated again. And another 5. So now we increment the count to 1. Now if we drew another 5, the algorithm would terminate and incorrectly report 5 as being the minimum of the distribution. But what happens is we draw a couple of 7s, which are irrelevant, and then we draw 2. So now we reset the count and we have a new, better candidate. And we draw another 2 after a few irrelevant samples. And finally, we draw 1. Fortunately, this happened before drawing another 2. And so once we've drawn 1, which is the minimum element of the distribution, the algorithm is guaranteed to succeed, to correctly report a 1, because there's no way that it can get confused with another smaller candidate. Okay. So here's the main theorem about confirmation sampling. And it says that if x1, so our nearest neighbor, you could say, is at least as likely to be sampled from the distribution as any other element, then the probability that confirmation sampling fails to report x1, fails to output x1, is at most 2 raised to the power minus t. So where t is the number of confirmations we require. So for t equals to 1, the failure probability would be at most 1/2. And this corresponds with what we saw before for the uniform distribution. So note that it's important that x1 is at least as likely to be sampled from the distribution as any other element. And this, of course, holds for the uniform distribution, where the max value is exactly as likely to be sampled from the distribution as any other element. Okay. And to sort of sketch the proof, I'll give you sort of the argument here. It's really not so complicated. You can just note first that in order for the algorithm to fail during its lifetime, it needs to have at least t false confirmations. And a false confirmation is when the sample is equal to the candidate and the candidate is different from the nearest neighbor, or the best point x1. So the algorithm has to have t false confirmations before sampling x1, because once it's sampled x1, it has essentially it's guaranteed to report x1 in the end. And now let's just look at this in the worst case. We can assume that beta is the second most likely outcome, x2. And here we'll use the notation P1 to denote the probability of sampling x1 and P2 to denote the probability of sampling x2. So what's the probability that we sample x2 before or oversampling x1? So you could say the only thing that moves the algorithm forward is either sampling x1 or x2. And this probability, based on our assumptions, is the probability of sampling x2 conditional on sampling either x1 or x2 is at most 1/2, simply because x1 is at least as likely to be sampled as x2. And then to extend this to several confirmations, we see that we have this probability of getting a single false confirmation to be 1/2, and then the probability of getting, t false confirmation in a row is at most 1/2 raised to the power t. And thus we have the theorem. So what are the properties, or why is this algorithm interesting? Well, of course, it's not so interesting to apply it to a uniform distribution because you need a lot of samples to identify the maximum. But for nearest neighbor search, we have these skewed or these sort of distributions given by locality sensitive hashing that allow us to sample the nearest neighbor with a much higher probability than more distant points. And we see here that the expected number of samples for finding the nearest neighbor, if the collision probability between the query point and the nearest neighbor is P1, then the expected number of samples is at most T plus 1 divided by P1. And this is because the algorithm is guaranteed to terminate when X has been sampled T plus 1 times. So compared to if we knew P1 and we wanted a specific error probability of actually finding P1. So if we knew how many buckets to look in, this is only 44% more samples. So it's quite competitive with could say an oracle that knew how far to search in advance. Just a few further properties. So it's robust to changes in the underlying distribution. So you could sample from different distributions. And it also actually works even when P1 is less than P2. So it just works slightly less well, you could say. Okay, so we're running out of time, so I will briefly skip through the remaining slides, which are about this adaptiveness, so knowing how hard to search essentially. So here we have this LSH forest we've been talking about, which is just an application of LSH to the dataset to split it into a number of trees, which are independent of each other. So it has some pretty standard properties, and we'll look at how to search such an LSH forest efficiently. So first we'll think of the setting where we have an oracle. So it essentially, the search procedure will result in searching a number of buckets at some depth in the forest. And the oracle tells us what's the collision probability to the nearest neighbor and how many points are expected to be in each bucket. So given this information, we know essentially how many buckets we should search, and the remaining question is what level should we choose in order to minimize the expected query time. So the expression for the expected query time is a bit complex, but it can be decomposed into lookups, similarity computations, and hash computations. And this graph here illustrates the number or the search time on a real data set where you can actually measure these quantities. So it's the search time as a function of the prefix length. So it shows that we want to hit the right prefix length in order to minimize the search time. And so this graph here plots the average search time if you fix the prefix length. And here we have it if we allow, or here we have the query time for each of 100 individual points. So there's some gain in adapting. Actually, it's a logarithmic scale, so there's a large difference in the difficulty of searching for these different points. So actually, there already exists a nice algorithm with theoretical guarantees which search from the bottom and then keeps track of the best candidate and stops once essentially the best candidate was expected to be found. So it proceeds, starts from the bottom, goes left to right, moves up, and sort of takes another layer of the forest. And this has nice provable properties. And I'll just briefly say that we do something similar in the paper where we use confirmation sampling for an adaptive stopping algorithm. And this avoids paying this order LK overhead of searching the entire bottom level. So it's essentially able to search at the right level from the get-go. And there are more details in the paper, but it's a fairly complex theoretical algorithm. So for practical purposes, I would recommend this adaptive stopping algorithm. To conclude, I looked at confirmation sampling, which is a simple stopping rule that gives you guarantees on expected recall. Then I talked very briefly about adaptive stopping, which is about adjusting the bucket resolution or depth to the hardness of the query. Some open problems. Can we apply confirmation sampling to other search problems? What about confirmation sampling for k nearest neighbors, not just the first nearest neighbor? Okay, thanks for listening.